Homework 4.2, Logarithmic Functions, Video 1. Homework due Friday, May 29th at 11:59 p.m. Alright, let's start this series of videos on logarithmic functions as I pace around the room looking for the good black marker that I was using just a moment ago. I'm sure it's here somewhere. It might be it. There's so many markers around here. As they kind of peter out, I just chunk them to the side. They're not bad, but for the purposes of filming videos, I want them to be as juicy as possible. But in the last series of videos, we talked about exponential functions, and here's an example of one of them. F of x equals 2 to the x power. Here's its graph. Here's the table of values that we use to generate the graph. The graph had certain features, such as having a horizontal asymptote on the x-axis. So y equals 0 is the horizontal asymptote, but only on the left half. It had a y-intercept of 1, which you can tell right here. There were no x-intercepts. The graph was increasing. Let's see, there were some other things we said about it. Oh, the domain was all real numbers because any number can be an exponent on the 2, but the range was only 0 to infinity because although 2 to the x can get as large as you want, it can get small but never hit 0 or go negative. But why am I bringing this up when we're discussing logarithmic functions, and for that matter, what is a logarithm? Well, I'd like to develop the idea intuitively instead of just saying, here is the definition of a logarithm, let's do stuff with it. In one of the videos in the previous series, I casually mentioned that this graph passes the horizontal line test, and as a consequence, this function should have an inverse. If you have forgotten about inverse functions in the horizontal line test, I recommend going back to the module in Canvas that was over homework 2.7, inverse functions, because I'm not going to reteach everything there. But this graph does pass the horizontal line test, which means if I can hit it with the horizontal line, I can only hit it once. And as a consequence, the function is invertible. So it raises the question, what is the inverse of this function, f of x equals 2 to the x? Or remember how an inverse function works. When you have a function that turns one number into another number, then the inverse function is supposed to take the second number and turn it back into the first number. For example, if I have a function that multiplies things by 2, so it doubles things, then to do the inverse, I would have to divide things by 2. So f of x equals 2 times x, and g of x equals x divided by 2. Those would be inverse functions. This graph, passing the horizontal line test, has an inverse function. So what is it? Well, I know what the values are supposed to do. Let's call this exactly what it is, f inverse of x. I know what this function is supposed to do, this inverse function. It's supposed to reverse what this function does, meaning if I give it 1/8, it's supposed to give me back the -3. And if I give it 1/4, it's supposed to give me back the -2. And so on and so on. If I give it a 1/2, it should give me back -1. If I give it 1, it should give me back 0. If I give it 2, it should give me back the 1. If I give it 4, it should give me back the 2. And if I give it 8, it gives me back the 3. So before we sketch the graph or define what this function is, let's think about this function as a question. Because a function really says, what do you want me to do to your number? This function, the answer to that question here is give me a number and I will raise 2 to that power. But let's think about a question where I give you this number and get that one back. And remember how this worked over here. Over here, these were powers that gave us this answer. So if these numbers over here were powers or exponents, then it stands to reason that they still are. So what question could we ask whose answer would be these in terms of powers? Remember, the original function was 2 to the x power. Well, I know 3 is the power that turns 2 into 8, because 2 to the third power is 8. So I guess a question I could ask is, what power do you put on 2 to get 8? This one. What power do you put on 2 to get 4? This one. What power do you put on 2 to get 2? This power. What power do you put on 2 to get 1? This power. And the same thing all the way up. What power do you put on 2 to get a half? A negative 1 power. What power do you put on 2 to get 1/4? A negative 2 power. And what power do you put on 2 to get 1/8? A negative 3 power. So it almost seems like whatever this function is doing, it's answering the question, what power do I put on 2 to get the input, which in this column is x. So keep in mind that whatever our function is, it's going to answer this question. What power do I put on 2 to get x? Let's graph this thing. I'm going to draw the graph here. I know the table's in the way, but honestly, it's not, and you'll see why in a minute. All right, so let's plot these points. Now, if you notice the x's, they're all positive, but they start out really small. And they go all the way to 8. So we'll go all the way to 1, 2, 3, 4, 5, 6, 7, 8. My outputs go between -3 and 3. Okay, let's plot these points. I go over just a little and go down 3. So I've got a point really close to the y-axis there. I go over 1/4, and I think I can cut this space into quarters pretty easily. Okay? I go over 1/4, but I go down 2, so right about there. This looks awfully familiar. I go over 1/2 and down 1. Wait, didn't we have some points previously that were hugging the x-axis over here? Now they're hugging the y-axis. I go over 1 and down 0. Hey, an x-intercept. I go over 2 and up 1. I go over 4 and up 2. And then I go over 8 and up 3. So if I connect these, I'm getting a big old deja vu here. I've drawn this picture before. This shoots off to the right, and this doesn't quite shoot off to the left. It takes a sharp turn, and it just kind of hugs along the y-axis here. Will it ever cross? Well, that's like asking, will the input ever be negative? Well, because it would be to the left. Well, that's like asking, would this output ever be negative? And no, because the range here didn't go past 0. So we may not know what the inverse function is yet, but at least we have a picture of it. But what about the asymptote? Does this graph have a horizontal asymptote? You might think it has one up here, but I'll go ahead and tell you that this will get progressively higher without end. And the reasoning is pretty easy. Look at the pattern here for the outputs. 0, 1, 2, 3, 4, 5, 6. I can make this as high as I want. The graph gets high as it wants. So it will go up forever, so there's no horizontal asymptote, but it does seem like there's a vertical one. And that makes perfect sense, because if you remember that these columns were the reverse of these, and these had a horizontal asymptote, now that they're y values, they have a vertical asymptote. But even this story isn't new, because this graph is that one, but reflected. How's it reflected? It's kind of tricky to see since they're not sitting on the same graph, but there was a relationship between the graph of a function and its inverse from back in homework 2.7. If you draw the diagonal line y equals x, and you have a function that's invertible, then the graph of its inverse is the reflection across that diagonal line. Again, not as easy to see since they're not on the same graph, but if you can picture this sitting there, they are mirror images across each other. So we seem to know everything about this function except what it is. We know its graph. It's got a vertical asymptote. What's that? Vertical asymptote is x equals 0, but it's only a vertical asymptote on the bottom half. What about the domain and range? Oh, wait a second, this was predestined. Part of the definition of inverse functions is that the domain of one is the range of the other. So if the domain of this one was everything, then the range of this one is everything. And if the domain of this one was 0 to infinity, if the range of this one was 0 to infinity, then the domain of this one is 0 to infinity, not including 0. This guy had a y-intercept at 0, this guy had a y-intercept of 1, this guy has an x-intercept of 1. Makes sense. When you form inverse functions, you switch the x and the y. So we know everything except what the blasted function is. Let me see how much time we've got on this video. Right about where I want it. So what is this function? Well, we have to make a new one. We have to make a function that asks the question or answers the question, if you have a base, what power do you put on it to get this input? And that function is a logarithm. In this video, we'll call it f inverse of x because we're talking in the context of inverse functions. But we're going to define a new function called log, short for logarithm, of x. Now, because there was a specific base mentioned, we need to mention it over here too. The place that you mention the bases in a logarithm is a subscript after the g. You would read this log base 2 of x. Log base 2 of x. And it is asking a question. And guess what question it's asking? This one. What power do I put on 2 to get the x? What power do I put on this to get that? In the next video, I'll define a logarithm function more specifically, and we'll talk about some special logarithm functions, and I got a whole list of things over here. I've got 7 videos planned, and then we'll talk about how to actually get the answer to a logarithm. But the key thing I want you to take away from this video is that we're inventing a new function called a logarithm, and the purpose of it is to serve as the inverse of this function. So instead of saying, give me a power and I'll give you an answer, focus. So instead of saying, give me a power and I'll give you an answer like this function does, the log function says, give me an answer and I'll tell you the power.